Okay, now time. Zakhar he is a man who concludes our school. So please, Zakhar, do it.
I conclude the school.
No, conclude with your lecture.
So, yes, hello everyone. This is the last lecture on random polytopes, and it will be devoted to a class of random polytopes, which are called beta polytopes, and they are defined in terms of beta distributions. I will explain in this lecture, I will explain how these polytopes are defined and how they appear in various questions of stochastic geometry. So here is the definition of beta polytopes. A beta polytope is a random polytope which will be denoted by P and D with parameter beta, and it is defined as a convex hull of n points, x1, xn, where x1, x2, and so on are IID points, random points in the d-dimensional space. So n points in the d-dimensional space, and they have a density which is a d-dimensional version of the beta distribution, namely fd beta of x. So it's a density in the d-dimensional space, and it is defined as 1 minus the usual Euclidean norm of x squared to the power beta in the unit ball. So it is a density in the unit ball, maybe smaller than 1. And of course, we need a normalization constant, which plays no role in the sequel. So some normalization constant times this number. Now, one can easily show that this is defined, that this is integrable for beta greater than -1. Now, this distribution has some interesting special cases. First of all, if beta is equal to 0, then we just have a uniform distribution on the unit ball. So we have a uniform distribution on the unit ball in d dimensions. What happens if beta goes to -1? Well, then this function converges pointwise to the function 1 minus x squared to the power -1, and one can check that this function is not integrable. So the function is not going to be integrable in the limit, which means that the constant converges to 0. We must have, so the integral of that converges to infinity, and the constant must converge to 0 for this reason. So pointwise, the function converges to 0. So all together, the whole function converges pointwise to 0. But the integral stays constant and is equal to 1 each time. And now what does it mean? We claim that the distribution f, or that a random variable with density fd beta, I will write it just as fd beta, converges in distribution as beta to -1 to the uniform distribution on the sphere, on the boundary. And here is the idea of the proof. First of all, by Haley's compactness theorem, the sequence of distributions with this density, or it's not a sequence, it's actually parametric family of distributions with these densities, must have subsequential limits, just because they are all concentrated on the closed unit ball, and the space of measures on the closed unit ball is compact. So there are subsequential limits. There are weak subsequential limits of this sequence. Now, any subsequential limit must have the following properties. So, I'm sorry, every subsequential limit is concentrated on the boundary. On the boundary, so on the sphere. This is because the function converges pointwise to 0 And moreover, it converges to 0 uniformly on every compact subset of the ball. So on every ball of strictly smaller radius, it converges to 0 uniformly, which means that there is no mass left there in the limit. So the subsequential limits are on the sphere. And now, why are they all uniform distributions? Well, for the simple reason that they are all rotationally invariant, because each FD beta is rotationally invariant, and so all the limits are rotationally invariant. So every subsequential limit is rotationally invariant. And since there is just one rotationally invariant probability measure on the unit sphere, the uniform distribution, it must be this holds, right? So this is the idea. So the case beta equals to -1 can be understood as a uniform distribution in some general sense on the unit sphere. And finally, the last case, beta goes to infinity, to plus infinity. What do you mean? What is the limit of that distribution if beta goes to plus infinity? Maybe after some normalization. Well, if I would normalize it and divide here x squared by beta and let beta go to infinity, and then the limit would be e to the power minus x squared. So one can guess that it should be the normal distribution, namely if say x1 has probability density f beta, of course it depends on beta, then square root of 2 beta times x1 converges in distribution as beta to infinity to the normal distribution, standard normal on RD. And this is most easily shown, so idea of proof, by applying Scheffe's lemma. Which states that it suffices to prove the convergence, the pointwise convergence of the densities, and the density is up to a constant 1 minus x squared divided by 2 beta. If we take the density of this x1 times square root of 2 beta, then it has this form up to a constant, and if we take it to the power beta, okay, it's to the power beta, then it converges to e to the power minus x squared half. And then one can also show that the normalizing constants converge so that we can apply the lemma. So there are at least 3 interesting special cases. And for example, if we are interested in polytopes where the points are just chosen uniformly and we then take a convex hull, or if we are interested in polytopes where points are chosen uniformly on the boundary and the convex hull is taken, then these are special cases. And the Gaussian polytopes are also special cases. And now this defines the class of beta polytopes. There is another class which is very similar and where all the formulas are very, very similar to those for beta polytopes. It's the class of beta prime polytopes. And it is defined as follows. So beta prime polytope is a polytope of the form PND beta tilde, which is defined as the convex hull of x prime and so on xn, where x prime, x2, and so on are IID random points in RD with density which is given by the following formula: fd beta tilde of x is up to a constant, which plays no role, 1 plus x squared to the power minus beta. And this is defined for all x in RD. So this is not concentrated on the unit ball. For example, if d is equal to 1, then this is something like the Cauchy density. So if d is equal to 1, then this is, and beta also, then this is a Cauchy density. And one can check that it is integrable for beta greater than d half, because we need here x to the power in the, so this should decay as x to the power minus d plus epsilon, or minus epsilon, and so beta should be greater than d half. So this is the class of beta polytopes. Now the question is how to compute the expected number of faces for these polytopes explicitly. Fk of Pnd beta tilde. And it is indeed possible to do it, so there are explicit formulas for both quantities, but this lecture is too short to explain it, and I will do in the following I will do the following. I will explain how these beta polytopes, or more precisely beta prime polytopes, appear in various problems of stochastic geometry. So I will show a number of problems, for example, on random tessellations, which can be reduced to these beta prime polytopes, and which may be of some general interest, because these two classes of distributions appear not only in stochastic geometry, but one may, for example, also ask whether we have seen in previous lectures, we have seen, for example, the appearance of beta distributions in tri-diagonal random matrices. One may ask whether there are beta prime tri-diagonal matrices, for example. I don't know. Okay, so let us now consider some examples where these distributions appear. One example deals with random cones in a half space, or random convex half on a half sphere. So we consider the half sphere as d plus, so it is d-dimensional plus, which means that it is in the d+1 dimensional space, and it is defined as the set of all tuples x0, x1, xd. There are d+1 coordinates such that the sum of the squared coordinates is 1, and the first coordinate is greater than 0. It is in R d+1. So, for example, if d equals to 1, then we have the following picture. Then we are in R2, and this is our half sphere. And then we do the following. We take random uniformly distributed points on this half sphere. So random directions, let u1, u2, and so on be IID and uniform on this sphere, this half sphere. So random directions, which are all in the same half space. By the way, this coordinate is x0, and these coordinates are all the others. So x1, xd. And so we take random directions, and then we take a cone which is spanned by these directions. So consider a cone Cn, which is the positive half of x1, xn, and it is defined as the set of linear combinations I from 1 to n of ui. I'm sorry, the variables were called ui. So u1, un, lambda I, ui, where lambda I are greater or equal than 0. So we take a cone spanned by these directions, this one. And then a question is, for example, what is the number of k-dimensional faces of this cone? Of course, in dimension 2, it doesn't make any sense, but in higher dimensions, it's non-trivial. And here is a claim, which was in some special case an observation of Barani, Hu, Kreitzner, and Schneider. In the following, by the way, I will usually not give precise references for the reason that some of the papers were written by a large number of authors. So I will just skip the references from now on. And they made the following observations, that the following somewhat surprising observation, that the limit as n to infinity of the expectation of fk of Cn exists and is finite. So what we are doing here, you may think of it as follows. We take random points on the half sphere, and then we generate what is called the spherical convex hull of these points. So the intersection of the cone Cn with the sphere is called the spherical convex hull. And the claim is that the number of faces of this spherical convex hull converges to some finite limit as n goes to infinity, which is strange because if you take the same thing in the, say, in the ball, in the disk, so take, say, uniformly distributed random points in the disk and let n go to infinity, then the number of edges or the number of vertices of this polytope goes to infinity. Here it is not the case. And let us give an explanation why this is not the case. Let us, so here is an explanation. Let us draw again picture. So here we have RD. Here we have just one coordinate x0. And then we do the following. We consider the tangent space to the sphere at this point, at the north pole. The tangent space is again d-dimensional. And then we project all the points, so all the directions, if this is, for example, v1, then we project it to this tangent space. If this is v2, it is projected to v2, and so on. Then we can consider, instead of this cone, we can consider its intersection with the tangent space, which is a polytope there. And we shall characterize this polytope. So the points ui are IID, which is why the points vi are also IID, and their density can be computed explicitly. I will just state the result. These points are IID in the tangent space, which we identify with RD, and the density is some constant divided by 1 plus x squared to the power d plus 1 over 2. So it is the beta density. It is the beta prime density, fd d plus 1 half prime. And a well-known special case of this situation is when d is equal to 1, then it is known that such a random uniform direction intersects this line at a random variable which is Cauchy distributed. And indeed, for d equals 1, we get the Cauchy distribution here. And what we have for general d is a sort of d-dimensional natural generalization of the Cauchy distribution. And now we have a beta. So in this section of the cone, so the section of Cn by the tangent space can be identified with the beta prime polytope. And now we have the question why the number of faces of this beta prime polytope converges as n goes to infinity. Now the reason is that the beta prime polytope itself converges in some sense. And we shall prove it by using extreme value theory. Namely, the beta prime distribution, recall that it has this form, is a heavy-tailed distribution. It has power law tails. It decays like a power of x. And that's why it belongs to the domain of attraction of Ricci distribution. But here we are in a multivariate situation, and we shall do the following. Let us consider v1, v2, and so on. So they have this density. And let us take let us divide them by n. So normalize. Consider v1 divided by n, v2 divided by n, and so on. Their density is the following one. I have to insert in the beta prime density, instead of x, I have to insert nx, because they divide by n. So it is nx squared to the power minus beta. But then in the density, there is also a factor here, because everything is d-dimensional. We have here a factor n, and then constant. And this is, if we now let n go to infinity, so x is fixed, and n goes to infinity, then this one plays no role. And we have here n to the power minus beta, and recall that beta is d plus 1/2. So we have here n to the power minus d plus 1 times n to the power d. So it is 1 over n times c over x to the power d plus 1. And now imagine, so this is the density of one point. Now imagine that we have n such points with this density. And we want to count the number of points in some domain. So for a Borel set B in Rd without 0, because maybe the reason to exclude 0 is that this doesn't hold for x equal to 0, right? So because then this doesn't apply. So for a Borel set which is here, we can try to count the number of points which are there. So the number of points vi over n which are there, I from 1 to n, has the binomial distribution with parameters n, because we have n points, and each point is in this set with the probability, which is the integral over this density, right? And I will just write 1 over n, or maybe I will write 1 over n in front of the integral, 1 over n integral over b of c x d plus 1 dx. And now we have a binomial distribution. The first parameter is n, and the second is 1 over n times some constant, which means that it converges as n to infinity in distribution to the Poisson random variable with parameter c over d plus 1 dx. So our process converges, or the set of the points vi divided by n, I from 1 to n, viewed as a point process, converges to a Poisson process. One can more generally prove that the sequence, or the sequence of points vi over n, if we view it as a point process, then it converges weakly as n to infinity to the Poisson point process with intensity given by that function on Rd without 0. So the points converge, and their convex hull converges to the convex hull of this point process, which means, so if we take the beta polytope, the convex hull of V1, Vn divided by n converges weakly in some sense which I don't describe. So in fact, it's a weak convergence on the space of convex sets with the Hausdorff metric. But I think it's easy to believe that if the points converge, then the convex hull of the points converges to the convex hull of the Poisson point process with this intensity. And now the convex hull of this Poisson point process looks as follows. We have here an intensity 1 over the norm of x to the power d plus 1. It decays as x goes to infinity, and it increases as x goes to 0, which means that there are many points near 0. So in fact, 0 is an accumulation point. Here we have infinitely many points. And then the density decreases, and one can show that there is a point with maximal distance to 0. So at some point we stop, right? There is a maximal distance to 0, and so we have a well-defined convex hull here. And this is the limit of the beta prime polytope. So the beta prime polytope generated by n points, and divided by n, converges to this convex hull weakly. And then it's also easy to believe that the number of phases converges to the number of phases of this limit polytope. So we can define the Poisson polyhedron as the convex hull, or let me call it PD alpha, d with parameter alpha, d is the dimension, as the convex hull of a Poisson point process with intensity, well, let's say 1 over x, norm of x to the power d plus alpha. Alpha is a parameter. And here we have a special case of this, and one, I hope it's now easy to believe. Of course, it's not a proof, it's some sort of weak convergence, but then we take functionals, so we have to prove that the functionals are continuous in order to conclude what I'm writing now. But assume it works, then the number of k-dimensional faces of the spherical polytope Cn intersected with the sphere converges in distribution as n to infinity to the number of k-dimensional faces of this polytope, of the Poisson polytope. And so we identified, essentially, we identified here this random cone in a half space. We identified its section with the beta prime polytope, and then we have shown that there is a limit as n goes to infinity in some sense, which is given by a Poisson process. This is the first example of appearance of Poisson of beta prime polytopes. The second example is the Poisson hyperplane tessellation. Poisson hyperplane tessellation. In general, a tessellation is a decomposition of space into polytopes which do not intersect in some sense and which fill the whole space. And a Poisson hyperplane tessellation is a particularly interesting example. It is generated by the Poisson hyperplane process. So let me first define the Poisson hyperplane process. You can imagine this process as a random countable collection of hyperplanes which are thrown uniformly in some natural way into the d-dimensional space. So it's a random collection of hyperplanes thrown in the space in the most natural way. And the construction is as follows. So it is constructed as follows. We need two steps. In the first step, we do the following. We take the d-dimensional space and we take one coordinate. So this is a line, and this is the orthogonal complement, which means it is d-1 dimensional. Now on the line, we take a usual Poisson point process of intensity 1. And we call the points R1, R2, R3. It's completely irrelevant how to enumerate these points. So this is a Poisson process on the line. Now, to each point of this process, we attach a hyperplane which is orthogonal here. So all these lines are in fact hyperplanes in general. They are d-1 dimensional. Now, what we constructed here is a Poisson hyperplane process in which all the hyperplanes have the same direction. So it's a non-isotropic. It's an example of such a process which is non-isotropic. Now, if I want to construct an isotropic hyperplane process, I do the following. I take any of these hyperplanes and rotate it in a random way, in a random uniform way around the origin. So this here is the origin, which, by the way, do not belong to the Poisson point process. So we take all these hyperplanes and rotate them in a random way. In dimension 2, this looks as follows. We take the first one, say this one, and rotate it, which means I take here a random angle, and the distance R1 is preserved, and then we take the line. So this is R1, and this is the first line of our process. Then we take R2, distance R2, and some random direction, and draw a line. Then we take distance R3, here, a random direction, and draw a line, and so on. And in this way, we get infinitely many, countably many lines in the plane. Now, in general, the same can be done for hyperplanes, and here is maybe a more precise version of this construction. So first, in the first step, we need distances R1, R2, and so on, which form a Poisson point process with intensity 1 on the real line. If you don't like the real line, you can also take the half line. Would give the same. And second, we need directions. I call them phi1, phi2, and so on, which are uniform on the sphere. So uniform directions on the sphere, and all objects are independent. So everything independent. And given these objects, we can construct the hyperplanes. The hyperplanes as follows. Hi is the hyperplane consisting of all x in Rd, such that the scalar product of x with the direction phi I is given by Ri. And then it's easy to see that this hyperplane is orthogonal to phi I because of this definition, and the point having distance Ri from the origin is on this hyperplane. So it's exactly what I tried to describe here. And now the Poisson hyperplane process. Poisson hyperplane process is then the collection of hyperplanes Hi to infinity. This is called Poisson hyperplane process, and if we choose phi1 to be uniform on the sphere, it is called isotropic. So it's maybe Poisson hyperplane process in its isotropic version. It would be also possible to choose an arbitrary probability distribution on the unit sphere, and then we would get something which is called a non-isotropic Poisson hyperplane process. For example, this construction is a non-isotropic process in which all the planes have the same direction. Now, one interesting feature of this construction, which is not clear immediately from the construction, is that the resulting collection of hyperplanes is stationary, or is translation invariant, which means that if all the hyperplanes are shifted by the same vector x, hi plus x, this is a shift of a hyperplane, then the result has the same probability distribution as the original collection. Well, this is not quite trivial because this construction was not really stationary. It uses the origin as the starting point, as a reference point. Now, why is it stationary? Just for the following reason. It is clear that this process is stationary, just because the Poisson process on the real line is stationary. So if I shift it, I get the same in distribution. So this is stationary. Now imagine that we take two possible directions. Now we rotate these planes, these hyperplanes, but we choose for each of them one of two possible directions. Now the hyperplanes for which the direction is, say, phi1 form a stationary process. So we will then have something like this. Here is one of the directions. Sorry. So here is one of the directions, and we get such a point process, which is stationary. By the way, it's stationary not only in this direction, but in every direction. And for the other direction, say this one, we get this construction. And it is also stationary, and they are independent of each other by the properties of the Poisson process. So for two directions, we get this union of two stationary constructions, which is also stationary. And now we can take, of course, any number of directions, say k directions, and we get something with like this, one direction, another direction, and one more direction. This is stationary for every finite number of directions. And in the final step of the proof, we can just say that the uniform distribution is a limit, is a weak limit of distributions having finitely many atoms. And since the limit of stationary processes is stationary, it should be true that this gives us something stationary in the limit. And now that we constructed this random collection of hyperplanes, we can construct the tessellation. The tessellation is namely the hyperplanes dissect the space into polytopes. These polytopes are called cells, and the collection of all these cells is called the tessellation, the Poisson hyperplane tessellations. So hyperplanes dissect RD into countably many polytopes which have disjoint interiors and cover the space. This is called the Poisson hyperplane tessellation, and we shall be interested in one of the cells, namely the cell that contains 0. So let Z D is the dimension, be the polytope that contains 0, the origin. It is called the Poisson 0 cell. And now we claim that this polytope can be related to a beta prime polytope. So we claim ZD is the dual polytope to the convex hull of the Poisson point process with the same intensity as before. So it is some constant which can be given explicitly to the power d plus 1. So I claimed it is dual to a beta prime polytope. It's not true. It is dual to the limit of the beta prime polytope, which is this one. So it can be, it's dual of the Poisson polyhedron. Now, what does it mean to be dual? So here is the notion of duality for polytopes. Let us consider some polytope P, and the whole theory works nicely if the origin is contained in the interior of P. And then we shall define the dual of this. So the dual polytope P dual, and this is given in the following way. So first of all, let us look at the polytope P itself. A polytope is a set of solution to a system of inequalities, of linear inequalities, if it is bounded. Now, the polytope P can be given by the following system of inequalities. It is the set of all x such that x times yi is smaller or equal than some ci, right? And let's say m are in Rd without 0. But since we assume that the origin is inside, the origin, so 0, should satisfy these inequalities, which means Ci should be positive. Moreover, it should be strictly positive because it is in the interior. And this means that I can divide by Ci, and I can write 1 here. So we can write here everywhere once. And then P is defined as the set of solutions to this system of inequalities. This has to hold for all I. So this is for all I. Now, the dual polytope, so P is a set of solutions to a set of inequalities, and the dual polytope is the set of inequalities which are satisfied by all points of P. So P dual is defined as the set of all inequalities such that are satisfied by this polytope, such that xy is smaller than 1 for all x in P. So set of inequalities satisfied by the polytope. Now it is clear that y1, ym are inequalities that are satisfied, so they are there. By the way, we identify here the space and its dual space. So we make here no difference because we have a scalar product and we don't play these games with the space and its dual. So these y's would be in general in the dual space. So they are in the polytope, and then P dual is just the convex hull of them in general. one has also to ask what is now the dual of the condition of this. So 0 is in the interior. What is the dual of that? And as far as I understand, it is that P prime is that P dual is not contained in a half space. So P dual is not contained in a half space. Because if it would be, then, well, then something would go wrong. One has to think about it. But anyway, we are considering the Poisson dual cell, the Poisson zero cell, and it is given by the following system of inequalities. It is ZD given as the set of all x in Rd, such that x multiplied by the random direction phi I divided by Ri is smaller or equal than 1. So it is exactly a form which we need to construct the dual polytopes, and that's why the dual polytope of the Poisson zero cell is given by the convex hull of the points phi I divided by Ri, I from 1 to infinity. And now, geometrically, we have the following situation. Here we have our distances. So R1, recall that R1, R2, and so on are distances. Maybe it's more convenient here to consider the distances without the signs. And they form a Poisson point process with intensity 2 on R plus. And so we have the following thing. We have R1, the smallest distance, R2, the second smallest, R3, the third smallest, and so on. And so on. And then we have these hyperplanes. And their intersection, so maybe here we have R3. And then their intersection is the Poisson zero polytope. Oh, I don't. This one probably. Now, what is the dual of this construction? The dual is that, and this is the origin. The dual is that we take the points phi I over Ri and construct their convex hull. So I have to, what is done here is just the inversion with respect to the unit sphere. If we take the unit sphere and take the inverse of these points with respect to the unit sphere, then these are exactly these points up to signs. And their convex hull is the dual of the Poisson zero cell. Now, R1 is the smallest number, so 1 over R1 is going to be the largest distance here. This is 1 over R1, it's the largest distance. Then the second largest is okay, it's 1 over R2, and so on. Right here, 1 over R3, and so on. We have many distances here which get smaller and smaller because these are the inverses of the points of a Poisson point process, maybe one here, and then we get something dual. Okay, maybe the picture is wrong because the dual polytope has to have the same number of, so the number of hyperplanes here or hyperfaces here should be the same as the number of vertices here. So if I have here 1, 2, 3, 4, 5 hyperplanes, I need 5 vertices here. Let me give here, well, let me draw one more vertex here. And there are here points. Okay, and now the question is, what are these points that generate the polytope? So here we know that the distances are Poisson on the real line, and what are 1 over R1, 1 over R2, and so on. Well, they also form a Poisson process by the transformation property of the Poisson process, and its intensity is the image of this uniform Lebesgue measure. And one can compute it. It is a Poisson point process with a constant over, it's even 2, by the way, but it doesn't matter, over s to the power 2 on the positive real line, on R plus. It's just the image of the Lebesgue measure under the transformation x goes to 1 over x. And then phi 1 over R1, phi 2 over R2, and so on, or maybe even without the signs, this doesn't matter. Form a Poisson point process on Rd without zero, with intensity which is given as follows. So this process on the half line is obtained from that one by taking the radial directions. And by taking the radial directions, we multiply the intensity by x to the power d minus 1. It's polar coordinates. So if we take the Lebesgue measure and take its radial part, then it has density x to the power d minus 1. So I have to divide here. And the result is that it is, I have to divide this 1 over s squared by s to the power d minus 1, and we get this intensity. So these points form again the Poisson process with this intensity. And we get that the Poisson zero cell is dual to the convex hull of this point process, which is actually the limit of beta prime polytopes. And now if we are, for example, interested in the expected number of phases of the Poisson zero cell, then we can use duality, and duality tells us the following thing. It tells us that each facet, so each hyperplane of this polytope corresponds to a vertex of the dual. And more generally, in any dimension, we have that that there is a correspondence, a bijection. So there is a bijection between the k faces of a polytope P and the faces of the complementary dimension d minus k minus 1 of the dual. So that, for example, a vertex here or a facet here, a facet corresponds to a vertex. And then in any dimension. And in particular, the number of facets here can be expressed through the number of faces in any dimension can be expressed through this one. So if we know how to compute the phase numbers of these polytopes, we know how to compute the phase numbers of the Poisson zero cell, which is one of the problems which motivated all these considerations. Now, a special case, let me mention a special case. Of this, it's a problem which has been considered by Remy and Zulanke. I think in the 60s, somehow, something like, I'm not sure the year is correct. They considered the following problem. They studied a random system of inequalities, defined in the following way. So they were interested in the solutions. Oh no. They were interested in the solutions of a random system of inequalities defined in the following way. Take a disk in the plane and then take random lines which intersect this disk in the following way. Take a distance which is uniformly distributed on the interval 0, 1. The disk has radius 1. Take just a random distance uniformly distributed, and then take a line which is and a random direction and construct such a line. And do this many times. So say here is another distance between 0 and 1, which is uniformly distributed, another direction, and here is another line, and so on. Yes, here it is like this, and so on, and so on. And now what they observed is that if we consider this polytope, so the polytope containing 0, the solution of random system of inequalities, let us denote it by Pn. They observed and they calculated that the expected number of faces of this polytope converges to pi square half and then goes to infinity, which is again somewhat surprising because the number of vertices does not increase to infinity. One could expect that it could increase to infinity at the first sight, but it does not. It converges to a finite limit. which is pi square half. Now, what is the relation of this model to the Poisson zero cell? It's easy to see. Let us look at the distances. So they are all uniform in the interval 0, 1. So we have n points in the interval 0, 1, R1, R2, R3, R4, and so on, the distances. And now we can form the order statistics. Let's call the order statistics R1, R2, R3. And it is known that if we take the order statistics and multiply them by n, because the distance to 0 of the first order statistic is of size 1 over n, because we have n points here, so its expected size is 1 over n plus 1 to be more precise. So it's natural to multiply them by n, I equals 1 n, and then it's known that this converges in distribution as a point process to the Poisson point process with intensity 1 on R plus. It's a known fact. And now if we take this picture and take a microscope which multiplies everything by n. So let us take a microscope which multiplies everything by n. Then what we see under this microscope, and we look at a very small neighborhood of the origin. Well, here we see nothing because there are no lines here in this very small neighborhood. But in general, we shall see lines, and the distances from these lines to the origin form a Poisson process in the limit. So in the limit, we see the origin, and then we see points of the distances which form a Poisson process, and then lines which are orthogonal. So in the limit, we see the Poisson line tessellation. It's in the plane, so it's Poisson line tessellation. And in particular, this polytope Pn multiplied by n converges in distribution on the space of convex sets in 2 dimensions to the Poisson zero cell Z2. And so the result of Rényi and Solanke can be interpreted as the expected number of vertices of the Poisson zero cell in dimension 2. Now the question arises how to compute the same number, or maybe even the number of faces in any dimension of ZD, where D is now any dimension. And I will not be able to, I will just state the formula at the very end of the talk without giving any hints how to prove it, because I think there is not much time left. So, but let me now continue by giving the last example of the appearance of beta prime polytopes or the Poisson polyhedra in stochastic geometry. The last example deals with another very well-known model, the Poisson Voronoi tessellation. So the last example is the Poisson Voronoi tessellation, or more precisely, the typical Poisson Voronoi cell. So it is constructed as follows. Consider a Poisson point process with intensity 1 on Rd. Now it is a point process, it's not a line process. The elements of the process are points. So this is Rd, a plane in our case, and we consider here points. And then imagine that at each point a crystal starts to grow uniformly with unit speed in all directions. It starts to grow, so it forms a disk. Here the same. Now at some point, these crystals start to meet each other. For example, if we take these two ones, so this one and this one, they meet in the middle, right? And if they meet, a boundary is generated between them. And then they stop to grow. And now what is the crystal of point Pi? So I denote the points. Points are P1, P2, and so on. And the crystal, or the cell of the point Pi, is then the set of all points in Rd, such that the distance to pi is smaller than the distance to any other point of the collection pi. So the distance from x to pi is smaller or equal than the distance from x to pj for every j. And each point generates a cell in this way. So here we might have something like this, something like this, something like this, here, and so on. And this is called the Poisson-Voronoi tessellation. So this division of space into such polytopes is called the Poisson-Voronoi tessellation. Now, what is the typical cell of the Poisson-Voronoi tessellation? By the way, one can define the zero cell here. So it's the cell which contains the origin, but we will be interested in another notion, in the typical cell. So the typical cell of the Poisson-Voronoi tessellation is defined as follows. Intuitively, it is the following. Imagine we have a window, but this window is not small as here, but a very, very large window. Then in this extremely large window, we have many cells, and we take them all and take a uniformly chosen cell from this collection. So if the number of cells is n, we take each cell with probability 1 over n, and then let n go to infinity. Let the window size go to infinity. The limit is what is called the typical cell. So it's just one cell picked at random from a very large window, intuitively. But of course, this involves some limit, and it's not easy to make rigorous. And that's why there is another definition, which is very interesting. It uses Poisson calculus, I think, and it applies not only to Poisson process, but to any point process which is stationary. So definition using, definition using Poisson calculus. Definition of typical cell. Using Poisson approach. It avoids any reference to limits. So this approach goes as follows. To each, let us fix some function which assigns to each polytope its center. For example, it may be somehow the left or the extremal corner is the in some sense. So the corner with the smallest coordinate, and then somehow lexicographically, or it may be the center of the largest sphere inscribed into this polytope, or something like that. The only thing which we require is that this association has to be translation invariant. So if we move the polytope, then its center moves according, together with the polytope. It may be, for example, the center of mass of the polytope, or something like that, any function. In our case, we do it in a simple way. We say that pi, so the point which generated the polytope, is the center. It's, of course, random here, but let's do it in this way. And then the typical Poisson cell, typical cell is the random polytope, which I call VD, such that its distribution is given as follows. The probability that VD is in some set A is a subset of the space of convex sets, is given as follows. We take any Borel set Q whose volume is not 0. So Q is a Borel set. Q, I'm sorry, in RD is Borel. Volume of Q should be strictly larger than 0. And then we do the following. We take here the expectation of the sum of overall I, for which the center is in Q, of the indicator event that Ci shifted by Pi, Ci is the cell, recall, Ci, I called it here Pi, of course, Ci Ci minus pi I is in A. So we do the following. We take a set Q, and then we take all the cells for which the center is in this Q. In this case, these cells. And each such cell gives a 1. So it is, if it has property A, then it is counted. If it doesn't have property, it is not counted. So each such cell gives a contribution to the distribution of the typical cell. But of course, this expectation is not, it's not 1, and that's why we have to divide by the volume of the set Q. Our process has intensity 1, and that's why I think it is a probability measure. Anyway, so this approach can be used to construct the typical cell in any stationary point process without referring to any limits. But in our case, it's very simple. We can just do the following. It is also intuitively not so difficult. So what is a typical cell? We take a very large window and take a cell uniformly at random in this window. And now imagine that the center of this cell is conditioned to be, say, at some point. Conditioning Poisson process to have an atom somewhere doesn't influence anything. And that's why we can just do the following. The typical cell has the same distribution as the set of all points, it has the same distribution as the zero cell of the Poisson-Voronoi tessellation generated by a Poisson process together with an atom at zero. So we do the following. We take Poisson process with intensity 1, and we add an atom at zero to this process. And then we generate the zero cell of it. Something. The claim is that this construction gives the typical Poisson-Voronoi cell. So it is the set of all x such that the distance to 0 is smaller than the distance to any point pi for all I. The claim is that this gives the same distribution as the typical cell. And now we claim that the typical cell can be related to the beta prime polytopes, or more precisely to their limits, to the Poisson Polyhedron. Namely, here is our claim, or maybe I will not write it as a claim, but I will just give the derivation. So let us look at this picture. We have here again hyperplanes at some distances. Now, if we have here a point, if this is the origin, 0, and this is some point of the Poisson point process, then we have a hyperplane here, which is orthogonal. And this is the middle of this segment. And for each point P1, we have such a hyperplane, right? And their intersection, or the intersection of these half spaces, I'm sorry, not like this. I don't need it. So suppose I have one more point here, P3, P2. Then we have a hyperplane here. And the intersection of these hyperplanes is our Voronoi cell, right? Now, what is the dual to this? The dual to this is obtained by inverting all these points, P1, P2, and so on, with respect to the unit sphere and taking the convex half. And now the only thing we have to compute is what is the, so I have to invert each point P1 to 1 over P1, right? To the inverse with respect to the unit sphere and take the convex half. And it's a calculation which shows that the dual is, that the intensity of the dual points is this time as follows. It is constant divided by x to the power 2d. So now it is a Poisson polyhedron with parameter alpha, which is now equal to d. So the typical cell of the Poisson-Voronoi tessellation is dual to the Poisson polyhedron with some parameter. And now the main question, or one of the questions which one can pose here is, what are the expected phase numbers of the, for example, of the Poisson zero cell or of the typical Poisson-Voronoi cell? And here I will just list some results which could be obtained using the tools, some of which I presented in the previous lecture, but not all, fortunately. So results on expected phase numbers. For the Poisson hyperplane tessellation. We can consider, first, we can take the zero cell in each tessellation. We can consider the zero cell or the typical cell. They are different in distribution. Now, if we take the typical cell of the Poisson hyperplane tessellation, then it was shown by Miles in the 1960s that it has the same expected number of phases as the unit cube. So it is just Fk of the unit cube in the same dimension. For the Poisson, for the zero cell, I mentioned a result of Renier and Solanke. Yes. I'm not sure the reference was correct. But I mentioned the result that this is pi square half in the plane. And now in general, we have the following formula. It is pi to the power k divided by k factorial, 1 plus d minus 1. And then we have some number a, dk, which is given by the following formula. It is the coefficient of xk. And here I would like to take here d minus k dimensional cell. It is the coefficient of xk in the following polynomial. 1 plus d minus 1 squared x squared, 1 plus d minus 3 squared x squared, 1 plus d minus 5 squared x squared, and so on, until we have here 1 plus x squared or 1 plus 4x squared is the last term. And this holds if k is even. So this is a formula which has been obtained recently. And it is an explicit formula for the number of cells here, for the number of phases here. In the Poisson-Voronoi tessellation, so first of all, for the zero cell, nothing is known, and it seems to be an intractable problem. No tools to do something about it. For the typical cell, the following formula has been obtained recently. So the expected number of phases in dimension d minus k of the typical cell is given by d to the power d over k times a gamma function or d plus 1/2 to the power k times, and now the most interesting part comes, the coefficient of x minus 1 in the Laurent series of the following function. Sine y to the power d minus 1 dy to the power d minus k divided by sine x to the power d square plus 1 if dk is even. And if dk is odd, there are more ugly formulas for it. Now, it would take too much time to explain how such expressions appear here, and maybe it would be also not very interesting for most of the
and that is your result, right?
Yes, for most of the visitors of the conference. Instead, I will explain just one piece of explain the reason why the beta distributions and the beta prime distributions are especially tractable. Moreover, it is possible to obtain explicit formulas for the expected phase numbers of the beta polytopes. And I will just explain the reason why the beta distributions are nice so that one can obtain explicit formulas here, because for other distributions, it's probably not possible. And here are the properties of the beta distributions. So the properties of beta distributions, of these multidimensional beta distributions and beta prime, of course, which makes them nice, which make them nice. The first property is the invariance under projections. Namely, if we take the Rk embedded into Rd just by taking the first k coordinates of a d-dimensional vector, and we take pi to be the projection, so maybe I will just write pi is a projection from Rd to Rk, just by retaining the first k coordinates of a vector, the standard projection, so orthogonal projection. And if x1 has distribution which is beta with parameters d and beta, then the projected vector has a distribution which is also a beta distribution with parameters k, because now it is k-dimensional. And here with beta something happens. We have to add the codimension divided by 2. So if we project and the dimension decreases by 2, then the beta parameter increases by 1. Each time the dimension decreases by 2, the beta parameter increases by 1. And one especially nice special case of this situation is due to Archimedes, whose result is as follows. If we take a sphere, of course in 2 dimensions, and inscribe it into a cylinder like this. I cannot draw it, unfortunately. I'm sorry for this very bad picture. Oh, no, it's not nice. I will not draw it. I cannot do it. I will draw just a section of it. So this is a sphere in dimension 3, and it is inscribed into a cylinder, right? Like here, right? But of course, this is cylindric, right? Then the surface of the sphere is the same as the surface of the vertical part of the cylinder. So the surface of the cylinder without these 2 caps is the same as the surface of the sphere. And moreover, if we take some slice here, if we take a slice, a horizontal slice, then the surface of the sphere contained here is the same as the surface of the cylinder for every horizontal slice. And it seems that the picture or the cylinder and the ball were on the grave of the Archimedes, and there are many pictures by famous painters which show the discovery of the grave of Archimedes, on which sometimes a ball and a cylinder are presented. And now this is a special case of this property of the beta distributions, namely, if we take the uniform distribution on the surface of the sphere in dimension 3, and the uniform beta distribution corresponds to the parameter -1, and we project it to a line, so the 2 dimensions are lost by this projection, which means that the beta parameter increases by 1, and which means that the resulting beta density is F10, I'm sorry, F10, it is in dimension 1. And what is F10? It's the uniform distribution. So the projection is the uniform distribution here. So here a uniform distribution on the sphere is projected to the uniform distribution on the segment, which is this result of Archimedes. And the same is true in any dimension d, by the way. We can take the uniform distribution on a d-dimensional ball and project it onto a space which has of codimension 2, and then the result is a uniform distribution on the unit ball there. So this is a more general version. And this property of beta distributions, well, is very useful when trying to do something with them. Now, another property of the beta distributions is the invariance under slicing. Namely, if we take a ball, and somewhere in this ball the distribution, the beta distribution lives, and now we intersect this ball by a hyperplane. Oh, sorry. Not only by a hyperplane, even by maybe even by any. Let's do it for hyperplanes. And the distance to this hyperplane is r, which is smaller than 1. Then in this section, we get a ball again, but the radius of this ball is 1 minus square root of 1 minus r squared. So let us enlarge this ball. Let us multiply this ball, or divide this ball by the radius. So multiply by 1 over this one. Then we get here a unit ball. The claim is that the restriction of the beta density to this smaller ball is again a beta density. So what we see here in the restriction is again a beta density, and the same holds for the beta prime densities. Now, how to see it? Well, the beta density depends on the distance to the origin, or the beta density depends only on the distance to the origin. So I can take this function, which is the dependence of the beta distribution onto the distance r to the origin. And now what we have here, say if this is h, or it's a bad picture now, let me remove this. So now if we have here distance r, and here we have distance h times square root of minus r squared, so that the maximum value of h is 1. So suppose this distance is like this, then p of this point, of this point x, or then the density at this point is given by the square root of p of square root of r squared plus h squared times 1 minus r squared, right? So this is that distance is the square root of this distance plus this distance squared. Or it is p of, or it is just inserted, it is 1 minus r squared minus h squared minus r squared to the power beta. And this is 1 minus r squared to the power beta, which is some constant. And I'm interested in the dependence on h, and the dependence on h is especially simple. It is again the beta distribution. So the slice here is essentially up to rescaling, again a beta distribution. Now, these two properties distinguish the class of beta distributions among all other distributions with spherical symmetry, and they, after applying them many times, make it possible to compute all these phase numbers and so on. Well, I'm sorry for not giving the full details, but it would be impossible in such a lecture, and I think it will be also not very interesting for most of you. So I thank you for your attention, and I think I'm finished at this point.